Thanks, Bjorn. That was a nice talk. So if anyone's got any questions, then the best thing to do might be to raise your hand in the button at the bottom, wherever it is. Reactions, raise hand. So if anyone could do that, that'd make it easier to sort out with questions. So before anyone does that, I just have well, it might be a simple one. Is there any simple explanation? Well, as in the answer, I think is probably no. But is there any simple explanation for why in the last problem channel flow has different behavior and is not memoryless, unlike the other examples you mentioned?
Oh, this is not known at all. I mean, we haven't even another paper I'm writing up at the moment, but I'll submit probably next week. But that's what I've been telling my student and postdoc for the last 3 months. Anyway, I submit next week. But let's see. It is rather counterintuitive, because if you do what many people did, simulation periodic boundary conditions, it looks so much like wet flow, or even in many ways like a 2D version of pipe flow. But there was a JFM paper, actually by a former student of mine in Baofan Song in JFM in 2019 probably, where he described exactly this process here. So he did some sort of hand-waving stability analysis of this leading edge here, and he found that there's this very regular growth process, which we had observed in our simulations as well. So that confirmed nicely that there's something else going on in channel flow at the leading edge, and at least at this distance from the critical point, this changes things completely. What I cannot say, if we go even closer to critical, so I mean, we know the critical point is somewhere around 640, 650. In experiments, we can go to 640 we manage, but the critical point will be slightly above. Then all we see, if we go even closer, the stripes will just leave our experiment, nothing happens. So we would need a larger experiment. In channel, difficulty is if you double the length, you also have to double the width. And we already, we have a 1 millimeter wide channel, 2 meters long, 50 centimeters wide, something like that. If you make it even larger, things start to bend, and even if you have thick glass plates and so on, you're not sure if you really have 1 millimeter. Is it now 0.9 millimeters in other places? It becomes experimentally very challenging, computationally equally it becomes difficult, expensive. So hard to say what happens asymptotically close to the critical point, I cannot say, but at least, some distance away from the critical point, where in other flows, everything looks like direct percolation, like in wet flow. In channel flow, it does not. So that's, I think, what I can safely say about it.
Okay, thanks. So I think Chris, you have a hand up first.
Yeah, okay. So can you hear me? Okay, yes.
Yeah, I hear you fine. Yeah.
Okay, fine. I've got a question about puffs, really. I mean, it seemed the whole picture on pipe flow is really very dependent on this concept of a puff, yeah? And I'm just wondering, first of all, I mean, presumably there's a whole range of distribution of sizes of puffs, yeah? And presumably the different sizes have different properties. But more generally, sort of how crucial is it, how general is the concept of a puff in different systems? I mean, you've already sort of indicated a bit that in channel flow, the puffs may be really rather different behaviors.
Well, it would be stripes. They are sort of two-dimensional then, yeah?
Yeah.
So the concept of a puff, okay, experimentally, it goes back to, okay, the paper comes to mind is Windianski-Champagne, 1974, so JFM, but there were earlier observations of that, but they call it an equilibrium puff. So there's a small range of Reynolds numbers, let's say between 1700 and 2300, where puffs don't tend to grow. So you create a puff, it will of course fluctuate in size, but there's a well-defined mean size. If you go beyond 2,300, and this is not a sharp value here, take it with a grain of salt. But if you go above that, then you get continuously growing structures for some time. They may break down into puffs again afterwards, but this is where what Windianski and co-workers would have called puffs and slugs, sort of some intermediate regime. And eventually you have expanding, nicely, cleanly expanding turbulent slugs at even higher Reynolds numbers. for many reasons, these expanding structures, for many practical reasons, I would say, are the much more important ones. And we also did some work on those. And there's, I should point out the nice work of Dwight Barclay on this. So, however, for this first transition, for the definition of the critical point, and for this non-equilibrium type phase transition, what happens to be what matters are only those puffs and these equilibrium type puffs. So this is a very small specific regime. I would say it's of academically certainly interesting, and you can link it to statistical physics, to universality class of phase transition, which, you know, at least kept me occupied for more than a decade, and you know, was fascinated by that, if that would work or not. However, from a practical point of view, you know, for engineers, let's say, this wouldn't be of much interest at all. You may be much more interested in when things really start to grow, and this is then sort of a different type of mechanism where Dwight Barclay had this description as an excitable media with where the front dynamics becomes important and puffs start to delocalize. You know, you have a leading front and a trailing front, and they expand.
Yeah. So that, I mean, in different circumstances, the sort of the behavior of the puffs is really rather crucial. I mean, what I'm trying to get at is sort of how universal is this transition to turbulence. What I'm hearing really is that it is really quite dependent on the particular situation, having a concept of well-defined puffs with particular properties.
Well, I would say, you know, that for this class of flows, it seems to be quite universal. However, you know, in channel flows things may differ, but in Couette and pipe flow, and people also look at even in Kolmogorov flow, I think, direct numerical simulations, and there was some annular flows also where very similar dynamics are observed. But what I'm trying to say is, you know, typically it's a small parameter regime where you get these localized structures, this localized existence between laminar and turbulent flow, and you have some sort of equilibrium where the turbulent structures can just about extract enough energy from the surrounding to sustain themselves, but they're dependent on the upstream laminar flow, typically upstream, to get enough energy to survive, but they cannot spread. So you cannot, you can never get fully turbulent flow in this small, you know, range of parameters. So I think the ideas as such are quite universal for shear flows, but only for a small parameter regime for each of these flows, I would say.
Okay, thank you very much. Thank you.